So good evening, everyone, and you're very welcome to our online evening lecture of the Republic of Ireland regional group of the Institution of Structural Engineers. Again, it's great to see so many attendees, and I'm perhaps not surprised that this is probably a lecture I've been looking forward to since this appeared out of the Collinstown Dublin Airport environment. Iconic now on the Dublin landscape. So I'm very pleased to introduce Sean Barrett, who's an associate in chartered structural engineer at Arup in their buildings team. He graduated in 1998 from UCD and has been working on I can't even say, like, a huge range of really quality buildings here and abroad, notably also Terminal 2, the Control Tower, UCD Science Centre, and also their new Futures project there. Following Sean, there's going to be Salam Al Sabab, who's also a associate at Arup. He's a structural engineer, graduated from the University of Baghdad in 1984, and from UCD with a PhD in 2012. And also he's worked on a huge range of projects, also lectures and teaches, I believe, in UCD on their part of their structures program, specialist in vibration, seismic and soil structure interaction. The whole point of these meetings is that we can share knowledge, I guess, and learn something, get an insight to the structures that surround us, and also the people that design, that are involved in the construction of them. So with that, I think there's going to be loads of lessons to learn from this. So Sean, best of luck, and you take it away, please.
Thanks, Paul, and thanks Victoria. Thanks for inviting us to give this presentation. It's great that we can do this remotely and that people can join in. Just to introduce myself, I'm obviously a structural engineer as my background, but in this project I also led a multidiscipline Arup team, which involved civil, structural, mechanical, electrical, facade engineering, lighting designers, geotechnical and environmental, and I think I've covered everyone. So we had a large team on this, and it's a team that we've assembled. This project we started in 2008, and there's many people that were involved in this project before me. So I think some of them are here as well tonight to listen into this one. Salam Al Sabah then is obviously very much a leader in our structural team, and Salam will bring you through some of the more difficult parts of the project, particularly around this wave stability and motion and dynamics analysis that we've done on the project. So just by way of introduction then, I'm going to give you a bit of a background to the project just before we go into more of the detail, just a bit about the client and a bit about the background to the project and the competition. Then I'll delve in and describe the structure and the foundations and the various aspects of the scheme. And then hopefully I'll keep everyone awake long enough to for Salam's presentation on the wind and dynamics and motion control, which is really the nuts and bolts of the difficult parts of the structure that Salam will talk you through. So if you can bear with me on that, I'll try and get through my bit. Just, I suppose, in terms of the client themselves, the Irish Aviation Authority, they're a commercial state-sponsored company, and the Irish Aviation Authority pretty much control all the aviation space around a large swathe of the Atlantic, 450,000 square kilometres of airspace, and they effectively control 90% of the east-west aviation route between Europe and America. So it's a very important air traffic service that they provide. They also regulate safety standards in Irish aviation, and also provide safety consultation to aviation authorities globally. I suppose just before, again, the purpose of a visual control tower, I suppose the nature of the work, I suppose in terms of air traffic control is in two parts. One is, sorry, just getting some feedback there. Thanks. On mute. Thank you. I suppose the air traffic control is in two. You've got the guys that work in that cover the air traffic from navigation systems, and then you've got the visual guys who work from the control tower and control this space around the aerodrome and above the aerodrome. So once a plane comes in close to landing or taking off, they're transferred over to the VCT guys. And they not only rely on their navigation systems, but visual contact is very, very important for an air traffic controller. And hence the need for a good quality air traffic control tower, especially in a very, very busy airport. The primary objective then is to maintain appropriate separation between aircraft. And that, as I said, requires really good visual contact. There has been debate about whether there is a need for control towers anymore with I suppose the advancement in camera technology, etc., and whether that could be done from via cameras. That debate is happening and still happens, but I think in recent times, I think about 2 years ago, one of the largest aviation near misses happened where an aircraft was misaligned coming in to land on a runway and was picked up by an air traffic controller in a control tower, and on a visual rather than on a navigation system. So it just proves again that the importance of the visual contact. So I suppose in terms of Dublin Airport, then Dublin Airport itself is now a primary international gateway to Ireland and to Europe. Lots of increased traffic over the last few years, and in 2000, at the time of, I suppose, the demand for this project grew in 2008. The passenger growth had exceeded 23 million. The Dublin Airport Authority were continuing to expand the airport, looking again obviously at increasing capacity and new runways, and therefore it needed a new control tower to actually provide services for this expanded growth. Again, the number of air movements per hour was at that time was about 48 movements per hour, and they're now looking to moving to an 80 movement per hour facility, and that then look to could the existing tower that they have in the aviation authority at the moment, could that work with this new demand for increased flights? And the answer was clearly no. They needed a new tower. So the Irish Aviation Authority then launched a competition, an architect-led competition for a new tower. And the brief, it was a very good brief that was provided, but I think some of the key words from that: it had to be safe and efficient. It had to be a unique and world-class visual control tower. It had to have an optimum working environment. The Irish Aviation Authority really put a lot of investment and value in their air traffic controllers, and they wanted the best-in-class facilities for those important workers, and they wanted a tower that would respect the relationship with the wider environment, i.e. the existing control facilities, the wider airport, and indeed the area and vicinity environment around North Dublin as well. And they wanted best in class in terms of ATC service, and a unique identity for the tower, that it didn't want something that was overly elaborate. There's lots of very elaborate towers, control towers in airports around the world. The brief was something for simple, elegant, but provided a focal point for people arriving in Dublin. So the team did quite a bit of benchmarking in terms of looking at international facilities, control towers, and a number of projects were looked at. Arup had just completed the new control tower in Heathrow, and I suppose that was a good example of, especially in the upper cab area. This is a different type of tower, and it was the structure of this tower was largely dictated to by site conditions. I suppose the cab was a good example of a good facility, a good design, a workable design. And so the team had looked at this project quite in detail, and that kind of started the concept for what we were doing in Dublin. Just at this point, I'd like to we'd key input from our aviation team in the UK, particularly led by Richard Matthews. Richard is actually he's led our global business, our global aviation business for some time, and has recently retired. But I just want to take the opportunity to thank Richard for his valued input into this project. You know, he's mentored the team, and he's always been available to give us the best advice. And our team and our client, I know, really appreciated that, and just want to wish Richard the best of luck in his retirement. And these are some of the images that of the actual of the Scott Talon Walker design scheme. So just some of the early concepts, just the sketches done by Michael Talon and David Cahill in Scott Talon Walker. And again, some of the early concept sketches through the pavilion building, looking up at the tower. So just a little bit about the site itself. I suppose it's obviously located close to Dublin Airport, and at the time in 2006, when the need for the control tower was emerging, the Irish Aviation Authority undertook a study of optimum sites and a number of options, and the height of the tower as well, given the position of the new runway and the expansion of the airport. And I suppose that study I suppose determined that the height needed to be about 80 meters high, and it needed to be centrally located in the airfield. And obviously locating it close to the existing air traffic control facilities was advantageous. So the site chosen for the tower, as you can see in the yellow dot in the middle of the screen, is directly beside existing conditions, and as you can see is centrally located close to the existing runway. And as you'll see, it's again very central to the second runway that is nearing completion at the moment on site. So it's actually it's centrally located, and again in the airfield, and gives good optimum sight lines across both runways, and indeed the aerodrome as well, or the area around the terminal. The other advantage of that site is actually that it's all landside at the moment, and that's hugely advantageous to anyone that knows working in airports. As if you go airside, it's a whole different set of difficulties from a construction point of view. So it was great that we were able to do that on a landside site. So this is kind of the site plan. As you can see, this is the existing air traffic control tower. Is located here, and this is the existing ATC building, and the new control tower then is located to the west of the existing facility, and that involved relocating a lot of services and the existing car park to the south of the site near the fire station, and introducing some new civils and attenuation facilities there as well. Then to just describe briefly the architectural scheme, I suppose is there's a number of components. The first is the base building, which houses predominantly a lot of the plant and equipment for the building, but also has manager offices and meeting rooms. Then that's linked by a tunnel, a services tunnel in the basement, and a bridge at the upper level to the vertical communications stem, which then supports the cab, which contains as a lot of the M&E plant for the upper VCR room, and also some staff facilities, toilets, etc., meeting rooms, and then the upper VCR, which is, I suppose, where all the magic happens in terms of air traffic control. And then just in terms of the plan, what that looks like in the basement of the pavilion building, where a lot of the plant and equipment is located, linked by service tunnels, 2 service risers up through the stem and up to the cab. Just would note as well is that there's quite a lot of plant and equipment here, because the type of building it is, it's of critical importance. So if there's a system goes down, there's always a backup system. So and a lot of protection to those systems as well. So a lot of flood protection around the building was introduced. So we raised levels, and also bonded all areas going into the basement, and then within the basement, if there is any kind of leak or whatever, there's a number of pump stations in the basement to actually get rid of any water that leaks in there. So lots of safety systems built in. And then at the ground level, again, you've got electrical equipment, backup electrical generators, etc., meeting rooms, and then you've got the link bridge back to the main stem of the tower. The main stem, then you've got 2 lift shafts, stair core, service risers, and just circulation space. And then at the upper section of the tower, then you've got I suppose the VCR at the very top, with I suppose the optimum sight lines set to the runway and critical points in the aerodrome. And below that, you've got security to access the VCR room, meeting rooms, and toilet facilities. And then with the level below, you've got various staff facilities, and at the lower levels, plant and equipment, and also your IT racks, supporting all the vast array of IT equipment up in the VCR room. And I'm not showing all the plans at every level, but this is just a layout of, I suppose, of what the VCR room looks like. It has 11 stations for air traffic control staff, and then within the center area of that, you've got the watch manager station, which looks out over, so it's the operation of the room, and that's linked by a stair from the lower levels. So then just moving on then to the structure scheme, the building itself, again, it's the base building, which is the pavilion, which is a single story flat slab structure over a single level basement, linked by a basement corridor and a link bridge. You've got the stem of the building, or the concrete stem, which rises up and then supports the 4-level cab structure and the 2-level VCR structure above that. And I'll just describe those individually in the next few slides. Just the tower itself is 88.3 meters from the top of the raft foundation to the top of the roof steel, which we believe makes that currently the highest occupied building in Ireland. I'm sure it'll be soon overtaken. And also the tower crane itself that was used to construct the building was a 100-meter tower crane. It was self-supporting, and the position of that was quite carefully located and agreed with the regulator and the aerodrome or the DAA staff as well, to ensure it didn't affect any of the flight paths in the area. So then just moving on then to the base or the foundation of the tower. So it's a 2.25 meter raft slab, and that's supported then on 36 900 diameter rotary bored piles, which are bored to rock and then have a 5-meter rock socket. And the reason, I suppose, why we chose such a long rock socket, so when we did our site investigation, our original site investigation, we discovered quite a rock head on the site. We then backed that up with a geophysics investigation and some rock probing to look at the condition of the rock. And what we found was that the rock head was really, really variable across the site in a very short distance. And aligned with that is the top of the rock was very was weathered, but also layered with a lot of bands of mudstone. So it kind of, what we concluded was it was in the kind of a geological feature or an area of two different types of rock meeting, and it probably wasn't the most ideal site to be landing an 88-meter tower, but we had to come up with solutions around how to get that to work. So I suppose the idea was that we would over drill the piles into the rock to make sure we got into a very good a base layer. We also then on site, when we we had an RE on site, and his basic job was to inspect the base of every one of those every pile that went in. So a camera was dropped down. If there was any doubt about what the condition of the rock was, there was probes put down through the rock to check, to further check the condition of the rock. And if we had to drill further, then that was instructed on site. The slide here just shows on the bottom left, I suppose, the varying lengths of the piles that you can see over the base of the tower. Some were in the region of 5 to 7.5 meters. That at the greatest, at the highest length, I think they went up about 20 meters. So that, whilst from a basic load carrying capacity, wasn't, you know, it was something that was solvable. It did come into our reckoning around the dynamics of the building, which Salam will go through with you in a few minutes, and how to model that. It became quite tricky. And that was important that we got that right. This is a photograph of the base itself under construction. As I said, it's 2.25 meters deep, concrete, and was the base is designed for its vertical load and horizontal load. It's also designed for the stresses associated with thermal and area age shrinkage. So we've not added reinforcement rather than trying to cool the slab under construction. We just introduced some additional reinforcement to control that cracking. You can see the starter bars then from the tower starting to, or the stem coming out of the foundation. So then the stem base, I suppose, is wider than the actual stem itself, and the reason for that is we wanted to try and transfer load out to more piles to actually stiffen the base and to actually to really reduce the movement and kind of control at the highest stresses. So you can see the dotted line is actually profile of the stem as it's coming out of the ground, with the stem itself, and then coming in from that inboard at ground level. Then the stem itself is, as was the design of it, at its minimum, the external walls are 300 mil thick and the internal walls are about 200 mil. And I suppose the design itself, or the geometry of design, was worked out, and it worked very well because we ended up with these kind of triangular shapes at the extremities, which is really where you want them from a point of view of, I suppose, controlling for stiffening up the stem and controlling that motion, and you have mass in the high stressed areas of the structure. Some other points to note on that as well is that the walls themselves were not straight. There was a curvature. I think the radius is like a 52-meter radius curvature, so that had to be built into the formwork for the tower. So the stem then itself, this is the photographs of the stem under construction, and it was a slip form construction, and we worked with the contractor to design the reinforcement to allow the slip form to go 24/7. So once it started at the bottom, it kept going, and it went from top to bottom, and it was a rate of about 6 to 8 meters per day. We also worked with the contractor to have a number of different types of concrete grades available. So if they wanted to slow down the rate of the slip, they would introduce a different type of mix, or if they wanted to speed it up, they'd have a number of different mixes to match I suppose, the speed that they wanted to go at. The as the slip form was moving as well, it was also laser guided from a point of view of tolerance. So I think in the end we got it within something like 10 mil of tolerance, which was amazing for the height of the building. The other thing that happened as well when we were slip forming this, we managed to just with the last kind of few meters of the tower as it was getting to the top, we got hit with the really bad snowstorm. And whilst the cab itself was heated, the slip form was heated and the temperatures within the slip form were being controlled, we just couldn't get a supply of concrete to the site, and they had to stop it for a few days, which was unfortunate because stopping and restarting a slip form, as everyone knows, is quite an operation. So that was just a piece of bad luck that happened on the project. But so then moving up the building then as well into the cab structure, which is I suppose the 3 levels at the top of the tower here. So the cab structure itself is a series of 12 Virindale girders that are cantilever, story height Virindale girders that span from the concrete core wall out to the outside ring, and in cross section, that's just the basic structure you can see is this is the core wall on the left with the story height Virindale girders spanning from the core and then transferring load by means of push-pull back to the core walls, and vertical load transferred to a corbel, which is located at this point, and they're radially located around the cab level 1, as we call it. So the base of the Virindale then is supported by this corbel, and because we went to a slip form type of construction, we had to come back and cast that corbel after the wall was constructed, and therefore we had to come up with a detail to include couplers within the wall, and then stitch on a series of U-bars back into the core wall post once the slip form was complete. And the design of that, I suppose, is designed then to load back into the core once the weight of the structure comes on. So in terms of, I suppose, the design then of the steelwork as well, because of the nature of the building, we determined that, I suppose, from a redundancy point of view, that this was a consequence class 3 building. That the consequence of a member failing meant that we had to look to alternative load paths to actually get this to work. And when we went through that, we looked at saying what would happen if a corbel failed, or a portion of a corbel failed, or a section of a lower Virindale collapsed. Where would the load go? And therefore we ended up coming up with a solution to introduce, for the redundancy case, a second Virindale at cab level 2. So in effect, we ended up with a double Virindale, such that if the lower one ended up collapsing in a redundancy case, this upper Virindale would actually work and support the building. We also introduced a series of vertical braces in the external perimeter to allow the lower level to work as a kind of a ring beam that would also transfer that load. So just looking at what that looked like from a kind of a fabrication point of view, we had our base. This is the base Virindale, which came and was bolted together on the ground and lifted in place, which I'll show in a minute. And this then transferred the load vertically and through push vertical load down at this point, and then a push connection back to the wall, and a pull connection at the top, which is achieved by means of a welded connection to a cast-in member in the upper wall, and then a second Virendale then was bolted and welded at the top here. So these were site welded connections, which took a lot of work and detailing to get right, and every one of them were were fully tested on site, all the welds, and a lot of quality control was put in place to make sure that they were right, and the weld procedures were fully signed off. This is actually the base of the Virendale as it lands on the corbel, and again we wanted to ensure that that load was actually located right in the center of that corbel. We didn't want it, off center, and also as the load comes on, we wanted to allow that rotation to happen without having introducing additional moments on the corbel. So we introduced a curve bearing plate underneath the connection point to ensure that we controlled how that load was applied onto the corbel. And the detail then was also allowed for tolerance in or out or whatever, or up and down, to get it exactly right. This is the cast-in section of the upper Virendale before the wall is constructed. So this is actually cast in to the wall as the slip form moved up past it, and you can see the plates on the outside are there to receive the welded connections for the Virendales, or the upper Virendale. And there's some of on the right hand side, you can see some of the photographs and the quality of the welds that were achieved on site, from the steel to cast in steel connections. Again, a lot of work and effort and testing to ensure that they were all correctly done. So in terms of then the construction then of this is what we call the donut lift, or the donut, which is actually the first level of Virendales on the cab structure. So the red members are actually just temporary members that were bolted in and just to keep everything in place, to lift this in one unit. You can see the vertical members that we introduced, or the vertical bracing members as well, that we introduced to ensure that, I suppose, the load is kind of evenly distributed, and that the longer Virendales, as they try and move more than the shorter Virendales, that the load is kind of shared between all the different parts. And this section was then lifted in one unit, lifted up over the top of the tower and dropped onto the corbel. Again, we looked at a number of analysis cases on that to ensure that that ring didn't move out of place as it was dropped in, that it was stiff enough to do that job without going out of tolerance. And again, this was more photographs of the ring itself being dropped down and guided into place onto the corbel. And then once that was in place, the next section of Virendales were bolted onto the lower one and then welded back to the concrete core. And then the next lift of steelwork for the cab was then bolted above that, and that formed the levels of the cab. Then moving up from there, we then have the VCR structure, the upper cab and VCR structure. So the structure itself for the VCR consists of 24 300 by 200 box sections. They were fabricated box sections rather than off the shelf, and there's reasons for that, which I'll come to in a minute. And there are 24 inclined columns which support the roof structure above. Those columns then are supported on transfer beams, which span from the central core back out to the lower cab structure and Virendale trusses below. And then the roof structure itself of the VCR room is an 18-meter span roof structure, 18-meter span trusses spanning from the inclined column to inclined column with a central ring beam in the middle to, I suppose, to enable the connections to happen, but also to allow an opening to access the roof above. And this is an image of what the just taken from the model, just to show the I suppose the trusses and the arrangement of the inclined perimeter columns. And this then is an image on on site of the roof structure under construction. It was centrally propped for the entirety of the construction, and it was the center beam was supported on the props, and then the trusses then were radially connected onto that central beam and connected out to the external columns. It was difficult to find an actual image that actually showed the roof structure, because once that was in place, the contractor put a deck system underneath to allow them to actually start to fit out, I suppose, the array of ceilings and lightings and services, etc., that go into this structure. So it was never really opened up as a wow moment to look at that steelwork. But this is kind of what, I suppose, what it looks like now. These are the inclined box sections. Sorry, 300 by 100 box sections. Sorry, I said 200 a minute. 300 by 100 box sections supporting the roof above. Now, these box sections are really important because not only do they support the roof and laterally support the roof, they also support the glass for the building. You'll see there's no mullion there, so the tolerance on that steelwork had to be really, really good, really tight. I think it was within 5 millimeters. So there was a lot of control in setting out and how those were positioned. They also contain a lot of the conduits and wiring that go from the lower level up to the roof level, to the communications equipment up there, and to allow for future cabling to move up to the roof. So we did a lot of work and testing. In fact, with the facade guys, they built a full-scale mock-up of that steelwork in the fabrication yard in Istanbul. The fabricators were a company called Metal Yapı. They also did the facade based in Turkey, and the team spent a number of days out in the fabrication yard checking and testing that this all fits together and works. That was and also the facade testing, load testing, water testing was done on these mock-ups as well. Another important part of the project, I suppose I mentioned the M&E. It's a very heavily serviced building. So a lot of the structure was set out. Our immediate scheme was looking at kind of, could we put cross members at the bottom internally in the plant areas, but really the plant areas are like they're nearly like car engines. They're really packed with services, and it's very difficult to, there's maneuvering space, but there's not much else room for anything else in there. So that really what generated the requirement for the Virendeels. But again, on the upper levels, the concrete setting out and the coordination of services, it took a lot of work, a lot of effort with the M&E team to get that right. And it was the beauty of modeling now, and BIM allowed us to really get that right and get that coordinated. Finally, just the one other last feature was that the lighting guys worked with the client to come up with a concept around lighting the tower, and we worked with the lighting guys to incorporate the kind of the strip lighting within the structure, and the connections back again down to the columns. I suppose the idea is that these lights can be changed color for whatever occasion. So if Joe Biden visits Dublin, I'm sure they'll light it up red, white, and blue. This was an image taken last year for Dublin winning the 5 in a row, and it's lit up blue. So it doesn't look like they'll be changing those colors anytime soon. But anyway, so I think that's it from my side on the background to the project. So I am now going to hand over to Salam, who's going to take you through, as well as the challenges of high-rise construction and wind and motion. So we're going to do we're going to try and do a virtual pass here. So I'm going to stop sharing my screen and sorry, Salam.
Yeah.
If I can,
You can
allow you to take over. You able to share?
I don't know. What can you see now? I started to share. Is there anything visible?
I'm trying to work if that's your screen or Sean's screen. So at the moment we can
Okay,
see the Teams window. I think that might be your screen, Salam.
Okay.
Do you want me to share mine, Salam, and I can drive?
No, I don't know. I mean, if you can see the this screen where we have loads and deflected shapes, etc. Can you see the screen?
We can't see that at the moment.
Okay. Let me try again to share my screen.
So if you stop sharing, yeah, that's your screen there.
Can you see it?
So if you hit the square box with the X on it and stop sharing for a second.
Yeah.
So, and now hit to share again.
Okay.
And just choose because you'll have a few different options to choose from. So if you select the presentation. Yes, we're in luck. Perfect.
Okay, very good. Thank you. So thank you, Sean, and thank you, Victoria. Now we talk about the journey that we took to design the most important part in this control tower. Control towers are tall because they need to be so due to their function. And because of that, they are considered to be high-rise buildings because their design is influenced a lot by lateral loads. Unlike normal high-rise building, where the section remains constant or reduces with height, in control towers, it's the opposite. The cross-section remains constant, but it is much larger near the top. Also, unlike high-rise buildings, where the top floors are known to be less comfortable than the lower levels, in control towers, the top level is the most important level because that's where everything, all the functions, the air traffic controllers, they stay there and they need to work in optimum working environment that we need to satisfy because that was one of the main points in the brief. So that was the challenge, and we spent a lot of time trying to solve that. And now, if you look to this screen, high-rise buildings are just vertical cantilevers. So there is horizontal load, wind load, in this case, and you can see that maximum shear force at the base is related to the height. So if the height doubles, then shear force at the base will double. Maximum bending moment, it's related to the square of the height. So if the height is doubled, the base moment will increase 4 times. We continue with the rotation, maximum rotation at the top related to the height cubed. But the important thing is the deflection at the top, which is related to the height to power 4. So every time we double the height, the lateral deflection will increase 16 times. Of course, horizontal acceleration, which is related to the comfort at the top level, is related to this displacement. So that is, let's say, the essential part that we need to solve in a control tower and in every high-rise building. So in Dublin, no earthquakes, fortunately. We have, on the other side, very good wind loads. So a wind load will have a mean variation of speed and pressure and fluctuations, which are the gusts. And we need to consider that in the design. So if there is a high-rise building and there is wind flowing in one direction, the building can move along the wind in the along wind direction or perpendicular to the wind direction in a crosswind direction. It can rotate also around the vertical axis in a torsional mode. So there are few odd consequences of winds affecting different profiles at different speeds. One of them is galloping. So in galloping, if we have a cross section that has sharp corners, say a rectangular section, or in our case, triangular cross section, inclined wind can cause lateral movement, in this case in the Z direction, and this movement will create a velocity component in that direction, in the Z direction. So the apparent, what is called apparent attack angle of wind, will slightly change, and this will start a reaction that you will see in this video. So this is a wind tunnel, and there is a triangular section. So you can see the wind blowing from left to right. And at a certain angle, this cross section is affected by galloping, and you can see the vibrations. And just now, the angle, the wind angle relative to the cross section has changed, and nothing happens. But because wind can't come from any direction, then that's not a very good solution. So the good thing is that galloping can be calculated to a reasonable degree of accuracy. So initial calculations, okay, we proved that critical wind speed is more than 105 meters per second, which is okay. So the conclusion is that galloping will not be a major factor affecting the design of the control tower. We have vertex shading as another phenomenon. So unlike galloping, which affects cross sections with sharp angles, vortex shading affect cross sections with smooth surfaces, circular, for example, where we have mostly laminar flow around this circle. So wind, in this case, on this circular section comes from left to right, and then at the back there is separation. The laminar flow stops, and there is separation between the wind flow and the cross section. And because of that, there will be some negative pressures resulting in vertices. So these vertices develop at both sides, top in this case and bottom of the circular cross section. And they develop at a certain frequency. This certain frequency is related to the shape of the cross section and to wind speed. Other factors, roughness of the surface, etc., let's say less important. So if the frequency of vortex shading generation matching a natural frequency of the structure, then this will move. So below here is a numerical simulation, but it is realistic. So you can see when wind flows from left to right, that at low wind speeds, nothing happens. As wind speed increases, you can see the generated vertices and the resulting lateral movement of the structure. There are some eye-opening experiences resulting from that. But in this case, we did our initial calculations. So this is velocity, and that's displacement. And we found that at a certain velocity range, there is a broad range of change. So instead of the curve moving smoothly as a, say, second-degree polynomial, second-degree curve, there is this bump in the curve between velocities, say, between 40 and 80 meters per second. And that is where we expect that vortex shading can happen. The calculations are very approximate. There is until now no closed form solution to it, but this is what we expect. Traditionally, let's say in chimneys, the solution, or one of the solutions, is just to try to spoil the laminar flow, the even flow, the smooth flow, in this case by these spirals. But of course, this is difficult to apply to a control tower. This video is just a demonstration of what can happen. So if there is a resonance, a matching in frequencies between the generating frequency of the vertices and the natural frequency of the structure, then this is the result. Now, I mean, as defined in the brief, and that was very important for us to satisfy, we need to provide optimum working environment for the air traffic controllers. And for lateral vibration due to wind, there is this standard, and the peak acceleration is determined by defining or determining the fundamental frequency, the first natural frequency of the structure. There are two curves defined, one for offices and one for residentials. So our aim was to have a performance that is much better than an office, and as close as possible to a residential behavior. The only problem with this curve is that at that stage, we don't know what is the natural frequency of the structure. So we don't know where we are on the horizontal axis. So that was our next aim, finding the natural frequency, through which we can then define the peak acceleration that is the aim of let's say, satisfying the comfort criteria. Now, to do that, to get the model properties, which in this case are two items. First, we need to find the natural frequencies with their mode shapes. And second, we need to find the modal masses, the distribution of masses as they move in that mode shape. Now to look to this problem, I mean, just to the basic components, we have a structure. So we know the dimensions of the structural elements. So we can find the stiffness. We have a foundation, piled foundation. All of that is fine, but all of that is founded on very unclear ground conditions. So that was our first challenge, to estimate ground stiffness. And next, we need to move and see the structural stiffness. By doing that, we can estimate the model properties, linking these properties with wind action and finding somehow the relationship between the two, so wind structure interaction. Then we can find the dynamic performance of the structure. Now, we collected all possible information around the control tower area, on the ground conditions, just trying to estimate the pile stiffness. And we ended up with such a diverse results. So from a minimum stiffness, from a minimum stiffness to a maximum stiffness, there was nearly a factor of nearly 10. So to say for sure at the design stage, where our information about the actual ground conditions were limited, what is the ground stiffness was very difficult. And that was the initial reason why we ended up with two solutions, an upper and a lower bound solution. So we picked one extreme and the other, and we worked from now in two parallel lines. So that is the workflow, which was a result of very good coordination between the structural and the geotechnical teams working on this project. So we have our structural model with the major structural components, all with their reasonable estimate of stiffnesses and material properties, dimensions, etc. Pile stiffness was based on, let's say, one extreme or the other, as we saw before. We can run an analysis, get pile reactions, but these are just pile reactions from a structural model. Soil ground is much more complex. It's a three-dimensional body, and with that, the piles work in group. One load on a certain pile will affect other piles. So the group action of the piles need to be considered in another model, a geotechnical model, which is in fact a three-dimensional model. It's a half-space elastic analysis with layers of different properties. So that is the cycle we took, getting results from the structural model, feeding that into a three-dimensional geotechnical model, getting soil properties, getting, as a result, revised pile stiffnesses, and feeding that again into the structural model and going into loops until we have converged results. Then we say, okay, that is the model that that faithfully represents, let's say, as best as possible, this condition. So that's one side. We did two parallel studies for both extremes, the upper and lower bounds. Then we moved on to the other unknown, which is the stem. During construction, this stem is affected by wind load. And as a result, at certain levels, if there are high wind speeds, high wind pressures, it can crack. So this is just one diagram of the studies. This diagram shows, the diagram on the right side shows all the parts that are in tension due to wind action. And a zone there at the bottom, you see this different color at the bottom, the light color, green, yellow. This is highly stressed area, in tension. So this area can crack. And this area is very close to the corners where we have our stiffness, where we have maximum area of concrete. If this area cracks, then we will end up with only the effective area of the reinforcement. So we will have a sudden drop in stiffness due to that. So that would feed also to our lower bound model, or if it is not cracked, feeds up to our upper bound model. In this case, we used a software called ADSEC, which does that. It's an Oasis software, which is quite nice and quite useful. So the two models, lower and upper bound models, have different natural frequencies, have different model masses. That's the first mode of one of these models. Now, with this information, we were ready to issue and complete and issue our specifications for the wind tunnel test, because now we have the model property, in fact, properties of the control tower. And in this specification, we specified the aims of the wind tunnel test. So at the end, we need to understand if vortex shading is important and how the damping affects the dynamic performance, let's say the comfort at the top level of the control tower. So now we move on to the wind tunnel test. So this test was made in the UK. RWDI is a well-known company, and this test, the wind tunnel test, requires the, let's say, creation, in this case 3D printing, of a very lightweight and stiff model. So in this case, that was PLA plastic. And you see these little holes. These are tabs where there are tubes inside feeding into pressure sensors. So at the end, we could have an understanding of the distribution of wind pressure coming from different angles. So we specified 5 degrees angle between let's say one run and the other. So that's the test sample with the important surroundings. That's the wind tunnel, and that is the setup. So this lightweight structure is supported on a support, a shaft that have 2 levels of strain gauges that will measure strain at these levels. So from that we can measure bending moment and shear force in all directions. All of that is supported on a gimbal that can measure twisting moment, torsion. So in fact, we can get 6 components as results, as reactions. All of that is done, great, and we have the results of both of the 2 models, the lower bound and upper bound, with 2 stiffnesses. The 1% damping, which we expect is the damping of the building as it is. It's a reinforced concrete building with very little partitions, so it's just a pure structure. So there are very few elements that can absorb energy. So this building has very little damping. So 1% sounds as a reasonable estimate of that. If we want to move up to improve this damping, we can go up to 3% or more, depending on what we need. So 3% was what we thought at that time would be a reasonable figure. The limits, acceleration limits, as per the standard that you saw, this curve at the bottom left, for both these frequencies, the lower and upper bound natural frequencies are as you see. So we fail if there is 1% damping. We're okay if we have 3% damping. So the conclusion is that we need to do something. This building will not satisfy the client's brief. It will not provide a comfortable and optimum working environment as it is. So now we need to move to the next step in our journey. Of course, we can get all the pressures, etc., etc. So the next step would be to talk to the client and see what they think. And this exercise is part of the journey that all of us took. I mean, ultimately, the end user would be the air traffic controllers, and they need to be comfortable and convinced that this control tower can provide good working environment. They will stay there for hours, concentrating on computer screens and outside from the windows. So our suggestion to the client was, why don't we simulate the possible vibration levels and let's see what the air traffic controller's opinion. So we did that. So we have a simulation carried out in Southampton University in the UK, and there is a platform supported on hydraulic jacks controlled by computers, and we can feed in any time history of movements. So we defined 6 sets of such time histories, representing a return period of wind from 1 week to 10 years, with 2 different damping ratios. The 1% damping ratio, the one that we believe is the actual structural damping ratio, and the 3%, let's say the improved one. And based on the results, and this is a nice animation of this room moving. So the air traffic controllers were inside looking to their laptops, sitting on a desk. And they, at the end of each one of these tests, they filled part of the form, giving their opinion about what will happen. about their feelings, sense of lateral movement. The result was clear that 1% was not good, 1% damping was not good, and we need to do something. We need to increase that to at least 3%. So the end result was that we then issued a new specifications for a tuned mass damper that requires the tuned mass damper to have a damping ratio between 10 and 15% of the critical damping, and needs to satisfy this damping ratio within this range of frequencies. We have initial calculations showing that we need 70 tons of mass to do that. And we thought a passive tuned mass damper is the best solution because it's more reliable. We have limited space, as Sean showed you. I mean, we have very little space in the control tower. So this is where we ended up at below cab level 1. So it's in level 18 of the stem, supported by cab level 1. So these tuned mass dampers were 2 here and there, suspended from the roof. So Vycoda is the company that supplied these dampers. So you can see a sketch of these dampers. So they are just a pendulum, inverted, let's say, supported at the top in this case. That's the pendulum. It's this mass. It's just steel plates, 35 tons each, suspended from these 4 rods. And at the bottom, you can see there is a pot, and there is a special fluid, special viscous fluid, and there are veins that move with the mass into this fluid, and that's how energy is absorbed. This is the damper. There are 4 vertical springs, small springs, and these are just to fine-tune the natural frequency of this damper. The rough frequency, natural frequency, is dictated by how long the 4 rods are. So by the time we issued the specifications, we didn't know what is the natural frequency of the control tower because it was still being constructed. We did not have any measurement. We have only calculations, the lower and upper bounds. So this is how a tuned mass damper works. This is a nice video. So you can see this pendulum. So it's a tuned mass damper. If the natural frequency of the pendulum of the mass, suspended mass of the mass damper, is made equal to that of the structure, then it will move in the opposite direction. See it again. And the relative movement between the structure and the damper then can be used to dampen the movement. In this case, the damper is only the friction of the vertical rod. But in our case, we have slightly better one. We have, in fact, much better one. Okay, so we waited until the last moment where all the mass of the tower is complete. So the control tower was nearly completed before we measured its natural frequency. So this test was done with a high technology piezoelectric accelerometer, very accurate, and it has 2 measurement directions, and these are the results. So the results were very close to our upper bound, and this is a proof that all the good things happened. We were extremely lucky that we ended up with the best possible scenario, the stiffest possible tower with the highest natural frequency. So that was the best we could have dreamt about. It's really very good. And this is just let's say a result of the good workmanship and dedication and quality control of everyone who worked on this project. I mean, from the design to construction, everyone. Now, incidentally, something, let's say, very unusual happened during that time, just before the dynamic test of the tower. You know that mobile phones these days have many sensors inside. In fact, all relatively new mobile phones have accelerometers inside. So as it happened, the resident engineer on the project, Joe Wade, was there one day with his lovely Samsung Galaxy Note 8, and he happened to have this software. You can download it, it's free. Physics Toolbox. And on that day, he observed that this light was moving. Okay, so Joe, we asked Joe, okay, record this movement. So he just put his mobile phone on a flat surface, and he recorded the movements. So that was just an Excel file, a CSV file. So with this file, we had a competition in the company, internal competition. Can you use the data and calculate the natural frequency? All of that was done before the actual test, before the company came and tested and found that the natural frequencies were this and that. And you can see that using this technology, mobile phone technology, we got reasonable results. That was, this movement happened because of Storm Diana. So that was the title of this article, describing what was done due to Diana. So that was one good outcome of Diana. So this high stiffness was a result that started with this quality control, piling, casting concrete, lift the stem, controlling every aspect of design and construction. We ended up with very good structure. And finally, we had the tune mass dampers arriving to site, because that the last clue was the natural frequency. Once we have that, we could then manufacture, let's say the manufacturing company like Koda can manufacture the 4 rods supporting the mass. And that's it, done, arrived, moving 35 tons times 2 upstairs all the way was not an easy task. Anyway, it was assembled little by little. Chains and hooks and all kinds of tricks were used. And here it is now, the control tower, working every day. Not every day, in fact. So we hopefully managed to, at the end, satisfy the client's brief. And from the dynamic side, that was the optimum working environment that we hope to achieve. So at the end, I have to thank everyone who was involved on this project, the structural team. So thanks to everyone. And our colleagues worked on this project, many of them since 2008. So it was a long journey. For many, it was a 12 years long journey. And at the end, thank you for your time and for coming to this presentation. Thanks.
Well, thank you, Salam and Sean. That's for an absolutely tremendous presentation. I think we have a tradition we started on the last event where we could people could show their appreciation by maybe all raising your hands together and then take it down again. We should see loads of yellow hands going up. I know if we were if we were meeting in person, there'd be great applause and cheers throughout the audience. So if everyone can just put their hands down, we're just going to go through the chat. I'm sure there are loads of questions. Lots of compliments. If people have questions, but by all means raise your hand, and we will. We'll be only too happy to. Perhaps waiting for people to raise their hands. A couple of things that struck me. And Sean, I loved your photograph of the sky hooks holding up the donut. And it's the first time I've heard in my career many people talk about sky hooks for structural engineers. And then you spoiled it with the second photograph when you see I think that was the mobile crane lift. Can you talk a little bit about that? Was that the biggest crane in Ireland? I think
it was actually. It was brought in actually from Holland actually, especially I think for that lift. I think Salam, wasn't it? I can't remember. It was yeah. Even the construction of that crane itself took a number of weeks actually to put the crane together. It was a large lift. And I think there was a good bit of organisation and a good bit of thought process went into actually getting that lift right. And I think myself and Salam were talking about that earlier. The contractors. We looked at a lot of pre-contract or in the design. We put a lot of thought in how you actually were going to build this, and with a number of options. And one of the options was to build a platform, a safe working platform that would be suspended below the actual cab structure itself. And I suppose the contractors then started to look when they got the project. I mean, they initially looked at the platform, then started to look at actually could we stiffen that ring and lift it in one, and that became the working platform. So that, I mean, the lift to do that, I think it was a brave move by them, but they really stuck with it. And also that was the main contractor BAM and Metal Yappy were the steel fabricators for both the steel structure and the facade. So they put a lot of work into that with us as well to get that right. And I think it worked very well at the end. Yeah.
Yeah, I thought the quality of some of the welding up there was really great to see. Was there much repair work that they have to do, or were they? They have tight control on it.
They had very tight control. I mean, it's funny in Ireland, we compared to Europe, I think there's traditionally in Ireland, site welding is we try and avoid it. And it was proposed. We had that discussion around this. We had originally again a bolted connection there with cast in, and and then they came back with a proposal to go with welded, and there was again a lot of thought and analysis went into that. But we went to one of the guys in the team, Shane Redmond, went to Belgium to look at a bridge lift that the same company were involved in, and to just look at their procedures in terms of the quality control and the procedures and and I suppose the qualifications of the guys that were doing those welds, and the method statements and the preparation they put into it. So they really actually were on their game with that. And then I suppose we then followed up with testing every single weld on site as well, which again there was nothing really defect wise discovered on that.
Yeah, and weather wise, I've had experience of site welding before where there was the weather had terrible problems trying to protect isolate the welder from the environment. Did you have, or the weather was particularly good during their time?
Yeah. Actually, the weather. Yeah, I mean the obviously we got hit with the blizzard that time. That really was a kick to the project because it did put a lot of things back. We'd gained a lot of time, or the contractors had gained a lot of time with the slip form, and then it was lost. And that last kind of with that snow, it stopped everything, and that was a bad news story on the weather. But then I suppose we had a reasonably good summer after that. But notwithstanding, the contractors had full enclosures protection around all the wells. Any well there was an enclosure built to actually work in and safely carry out that work.
Okay, thank you. I've received some questions in from Una Began, who's our vice chair of our regional group. So really enjoyed that and learned a lot. Was the curve in the middle of the elevation for an aesthetic requirement only? Did it have a significant impact on the design, or was it more awkward to deal with? So the curve in the each side of the elevation, on the curve on plan, the slight was it a 50-meter radius curve?
Oh, okay, sorry. In terms of actually, no. I mean, it obviously I suppose added to the complexity of the slip form. But the slip form was just built. It was just fabricated with the profile of the concrete built in. You know, so it was just, you know, the Beach Now, the slip form company, they manufactured that specifically for the project, and it worked really well. Yep. And
did it maybe for Salam? Did that have any effect on your wind your CFD models, or did you model those curves, or did you just assume straight edges?
The model was very faithful, but from the design side, I mean the curvature was, I mean, you know, the radius was more than 50 meters, was 52 nearly meters, and with that the horizontal reinforcement were not required to be bent, because it was a very mild curve. Yeah. So they were brought to site as straight bars. So it did not affect the design much.
I think the architect, there is an architectural reason for the curve to do with the white panels and the reflectivity of light. I think they were trying to optimize that, or there's some trick by curving. They were getting better kind of reflective kind of appearance to the building. So I'm told.
Okay, great. So more compliments through there again from Joe Kindregan, actually past president of the institution. Excellent presentation of what will be an iconic structure for many years. Sean, does the strip lighting have the Mayo colours?
I hope it does, Joe. Yeah, I hope it does. And I hope it has the Wexford colours too. For some, we might be waiting a while for them. Hopefully, Mayo will sorry for the Dublin people on, but
yeah. From another question here from Richard Matthews: do the air traffic controllers like working in their new tower, or do they suffer from vertigo? Or is that a factor?
I think the air traffic controllers are used to the existing, the old one, which was less than 1/3 the height of this control tower, the new one. So the height is well, it is a lot higher than what they used to do before. So possibly.
I think just one thing I just add. I mean, great to hear from Richard there. But in terms of and it was good advice that was given at the time, is that because of the nature of these structures, they do move, and it's about actually educating the end users. Because if you're working at 85 meters up in the air in a very windy, stormy condition, very adverse condition, it's not a place you would want to be or feel comfortable with a lot of motion. And even a small bit of motion, that you know, once you're anticipating that and understand it, it's not a problem. But it's just, if it's a surprise, then it is a problem. And I know there has been issues with other control towers around that area. And I think again, when we visited the control tower in Heathrow, it was interesting to hear the feedback from the guys there, was that they knew when the damper was kicking in. They could feel it. You know, they'd feel the first shunt, and then once they'd know, they'd feel safe. You know, they'd know everything is working. You know, so it's about and again, you know, that experience that Richard brought to the team was actually kind of, you know, you need to bring the client on that journey, because it's really important.
Yeah. So the design was specifically to address that aspect. They address the aspect of the lateral movement and lateral acceleration and the comfort in that direction. I mean, we know now that 1% of damping, which is the structural damping, is low. And the supplemented damping provided by the tuned mass dampers will increase that to 3.5%. At that level, it would, the comfort level would be very close to a residential environment, which is quite easy. But we need to remember that this is an 88-meter tall building. So comparing that to the old control tower, it is more than 3 times taller. And as a result, just from simple calculations, it will move, it will deflect, just static deflection, more than 80 times more. So that is just the static component of lateral deflection. There is no dynamics now, it's only static action. But static deflection do not produce the feeling of movement unless there is a target. The eye can focus on that target and can sense this movement. And because all traffic controllers are far from this target, I mean, they are at more than 80 meters height, and their targets is at the airport landing. So this distance will not be enough for a person to detect by eye this movement. So from a static point of view, no, there will be no feeling of lateral movement. From a dynamic side, there will be very little feeling because the tuned mass dampers will reduce the movements to barely this limit of sensing them. That is nearly the residential vibration limit.
Excellent.
Just to answer Richard's direct question directly, no, we haven't actually got any feedback from them, but I'm no doubt we would know very quickly if it wasn't meeting the performance, you know. But I think it's probably we watch that for the next few big storms that come in. Yep.
Okay, just a few more questions here from Paul Coughlin. Did the wind test show compliance with the wind code forces or give you savings?
The wind test results were finally used in optimizing the design of the cab. The cab, as Sean described, had very little structural elements. There were only 24 rectangular sections supporting the VCR, the visual control room. So we managed to use the reduced wind loads for the cab. So it was used to optimize the structure, yes.
It was also used to optimize the facade as well. The pressure sensors, I think the guys were able to justify some lower loads on some parts of the facade systems, but also there was a concern around the smoke extract system. Whether in a high wind environment, would the pressures be so great that you couldn't actually extract this in a fire and high wind environment? That if the smoke extract system couldn't, if the pressures weren't right, it couldn't release the smoke outside. So I think that was actually it justified that design as well. That the pressures were checked and found to work.
Okay, great. There's a few more questions. Are you happy to take a few more? Mike, just I'm conscious of the time for people. I'll try a few more. We have from Paul Murphy, again, enjoyable presentation. In relation to the pile stiffness, were your upper and lower bounds estimates made in advance of piling on site, or were they based on site tests, pile tests?
No, at the time when we completed the design, these were just based on available information. So they were not based on test piles. The test pile came much later. So by the time we had the design completed and our upper and lower bounds for stiffness made ready, we didn't have any test pile information.
Okay. Joe O'Brien, were dampers at other locations considered? I was wondering about the possibility of floors on dampened sleds within raised access floors. Or if you wanted to show off the VCR constructed as a parallel pendulum within the main structure.
In fact, I mean, the answer is yes. So, you know, this project is not new. We were thinking about possible positions for the tuned mass damper since 2008. And during the 12 years, we had many options, many ideas, some of them less crazy than others. One which is used in chimneys is to have a ring suspended outside the chimney. So we thought about a similar option where we have a large steel ring on part of the cab, but the space was so limited that it needs to be outside the cab, so it was exposed. And at the end, we decided that this is not a good option because of concerns about durability of this damper. If it was a chimney, then yes, I think we could have done that. But in a control tower, maybe that's more difficult.
Okay, very good. What was the maximum lateral deflection of the tower?
I don't remember now. I don't know. Yeah,
okay, no problem. From Darren Noble, again, of our committee, when the client's comfort levels were surveyed in the dynamic test rig in Southampton, were you able to benchmark their reported comfort levels with previous studies? And he's thinking of displacement and acceleration criteria for stadia and the like.
Yes, I mean, so the answer is yes, but I mean, we need to remember that this is just for lateral movement due to wind action. In a stadia, the vibration is vertical, and it has, let's say, people have different sense of vertical motion relative to lateral motion. But yes, I mean, it was as a principle, yes.
Okay, with that, I think I'm just going to make one comment that came in from Noel Sheridan, before I ask Orla Mannion from our committee to give a vote of thanks. It's from Noel Sheridan. He says, great presentation. Really like the first principles explanation to the design and enjoyed the video showing dynamics in real life. And I think many of us here would wholeheartedly agree with that. So I'd like to ask Orla to turn on your video, please, and
I should have it on.
Thanks. Yeah,
I'm on.
Great.
Okay. So yeah, Paul asked me to give this vote of thanks because I've previously worked with both Sean and Salam. Hi, guys. It's nice to actually be nicer to see you in real life.
Yeah, exactly. It's nice to see you. Yes, in real life.
Yeah, so I've never given one of these before, so I'm going to keep it brief, and I've written down just a few points about what you were saying and trying to summarize a few little things. First of all, I think like the client's brief said it wanted a unique world-class visual control tower, and I think most people can say that you have definitely achieved that. Personally, I can't wait to get back to Dublin Airport and see it outside a plane when I'm going somewhere again. I really enjoy seeing it when we're there. I think both of you highlighted the importance of quality, and not only in the design aspect of it, but in the construction side of things, and the tolerances with the slip forming, the really good weld quality, the piling and the raft foundation, and how important that is, how like it would be a very different natural frequency at the end of the day without that quality. So I think that was one point that really came across. Sean talked about the Verendale trusses and the corbels. and the way the corbel has been constructed outside the slip forming. I know there's a load of couplers and things that went in there which wouldn't normally be considered. What else? So I found very interesting about the snow that, like, the best laid plans, it cannot account for nature. Like, it's great that it didn't have an adverse effect on it, but it's something that we never, like, that you wouldn't consider the extreme snow conditions, especially in such a massive project. So that to have little to no effect in the end is a great outcome. Salam talked about all the great theory that brings back a lot of memories. And so I know, like, the various wind actions that when we work on low-rise things, you never really consider. It's great to see those sides of things and to get a proper understanding of them. I suppose the big thing is it always comes back to the human aspect. You can do as much soil interaction with the piling and with the natural frequency and with the damping and the vibrations, but it all comes back down to the human aspect. So it was really interesting that the control tower operators got to go in and give their input in it, which I suppose is not something we'd normally get to do, but it's really nice to see that and to get feedback on what the actual working environments are. Again, also the natural frequency, the fact that it was the higher rate of it when it was tested. Again, not something we'd normally get to see in reality. It's normally a very theoretical thing. So it's a reassuring aspect that, yes, the theory does add up to something. It does give you the correct answer. So again, it's very interesting to see that. And yeah, I personally don't really want the Mayo colors on the control tower. I'm not a Dub either. I'm a Roscommon person, and I don't want either of them, to be honest. But I can't have it that way. So yeah, I think yeah, that's it. On behalf of the committee and I suppose everyone here, I'd like to say thank you. It's lovely to see both of you, and yeah, thank you very much for the presentation.
Thank you.
Thank you, Orla.
Thank you, Orla, and I just like everyone. Traditionally, we can all raise our hands, or if you want to switch on your microphones, you can hear hopefully hear us clapping. So I don't know how well that. And with that, I'd just like to thank Sean and Salam again, and all your team at Arup, and all the people, diverse group of people who are involved. Very well done. I'd highly recommend to people that there's a road that goes past around the back of the airport, which actually drives by the base of the tower within, I don't know, 20 meters or something like that. You can do a drive by. It's pretty inspiring to go and actually see the scale of this pretty up close and personal. I don't know how long that road is going to be open with developments at the airport, but time will tell. So with that, I think I'd like to close the meeting. We'll have a new program in the new year, and with that, this evening closes our 2020 session, and we look forward to hopefully meeting in person again at some stage in 2021. And with that, I'd like to wish you the very best for Christmas and the prosperous new year. And thanks again to Sean and Salam. Thank you.
Thank you. Thank you.